Okay, good morning. We're going to solve this example problem for this homework. Real briefly, the homework is going to involve applying the principles we've learned of having, you find the force, you find a new momentum, find a position, repeat. This is what we're trying to program, but we're going to do this day by hand just to get some practice with this. So there's 3 practice problems in it. The rubric will be online. So here's how we do it. Again, I already have found the net force, so the next step is to apply the net force. And you remember the net force is, as we have defined earlier, net force times time unit. In all these cases, the time unit is 1, just to make the math easy, is the change of momentum. So that's going to be the change from initial to final. So all I need to do then is, here's my object, here's the net force, 3 units down. So here's my momentum initial. And so applying net force to that over a time unit of 1 gives me a final momentum in that location. Cool. So I've applied the net force to the momentum, and it has changed the momentum. The momentum has shifted down because there's a force being applied to it. Now, step 2, find the new position. We notice that the mass of the object is 2 units. And we remember that momentum is defined as velocity times mass. So to find the new position, right, we need to move it along its place by again, let me put this a different way. If you have an object here and you apply a velocity here over a time unit, the new position is here. So that's, right? And if you apply the velocity again to this object, that's its new position, right? That is in terms of defining it. If this is our, position vector, here is our new position vector, right? Our position vector is just changing as a velocity because, again, velocity is change in position. So the problem is we don't have a velocity, we have a momentum. So in order to get a velocity, we just need to divide by mass because we know that momentum is defined as mass times velocity. So therefore velocity is momentum divided by mass. We notice the mass unit is 2. So therefore, how far will the ball move? The ball will have moved half the new momentum. So I'm just going to eyeball it for today. And you guys will have a ruler or do something like that. So if half looks about right there. So that's the new position. Okay. So we're not quite done yet. That's good. Now say I want to set this problem up again and go a couple more cycles. Well, the first thing I need to do is, let's get rid of the information we don't need. We don't need all that information. But the object still has its momentum, its new momentum, in this direction. And on inspection, I notice that momentum is going 3 down and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 over. Again, I'm totally cheating by using graph paper. That's totally okay. So we're going to go 3 down and 13 over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? So our new momentum starts from here. It goes to this point. That is our new momentum. Again, just going to get rid of the extra information we don't need. Okay, so here's our new momentum. All right, let's go another cycle. All right, we're going to assume on all these problems that the same initial net force is a constant. So again, this is net force is in 3 down in that direction. That's what. So here is our old momentum. And that would mean our new momentum is right there. This is our new momentum. Okay, pretty cool. Again, because the mass is 2, we're going to move. If the mass was 4, we move a quarter. If the mass was 3, we'd move a third. If the mass was 5th, we move so if the mass was half, we would move twice, right? That's how this works. And so we're going to, again, move the object. Let's say that's halfway there. I could cheat a little bit here, and I notice, oh, look, the momentum is going to be somewhere along that line. We know the new momentum is going to be somewhere in line there. So all I need to do is figure out how far down it's going to go. So that's 1, 2. So here's my new momentum point. Let's do that in yellow. Yep, right. And yep. So 1, 2, 3, 4, 5, 6. All right, the new momentum is going to be 6 down. So 1, 2, 3, 4, 5, 6. And come over because we, and there is our new momentum. Again, I'm just going to get rid of, you won't have the luxury of being able to erase as easily as I do, but I can. Okay, so there's my new momentum. One more time, just to make sure we get the point across, right? Get rid of let's get rid of the extra information. One more time, just make sure we have the point across. All right, so again, we're applying a constant force in that direction. All right, so we've calculated the net force. We apply the net force, which then changes the momentum. Right, here's our old momentum. Here's our new momentum. Right. Okay, so now we know the new momentum. Now we need to find a new position. And position is not changed by momentum, but by velocity. Velocity is momentum divided by mass, which is 2 in this case. And so we would change our position vector by our momentum. So our velocity, like if I went ahead and drew the velocity vector would be here, right? That is the velocity vector. And so what's going on here is, again, if we take our origin, coming back all the way to our origin, let's go in purple, right? This is currently our, let's not use P, this is currently our initial position vector, right? And so therefore our final position vector would just be this right here, which is our, excuse me, would just be this right here, which is our velocity times our change in time, right? Just like our change of momentum is our net force times change in time, right? But in both these cases, our change in time, conveniently, we have set as 1. If it was different, you would have to go and take that into account. But all this means is that the new object's position is right there. So you can see that this ball, as predicted, is taking a nice, and we can even predict the curved slope this would take. All right, so that is how you will be needing to do this homework.